Hello, I'm Seema and welcome to part 6 of the chapter, The Solid State. It is now time for us to understand close-packed structures. We have understood that there are different types of unit cells and there are 14 different types of Bravais lattices that we've understood now. Let us now see how these atoms are arranged to form solids. And we know that in the case of solids, the atoms or the constituent particles, whether they are molecules or ions, they touch each other. So we imagine these constituent particles to be spheres, and for the sake of simplicity, we imagine these spheres to be of identical size. And then we see how many different types of solid structures or what are the different patterns or arrangements that are possible. So let us begin with it. The first thing that we see about a close-packed structure is we first have atoms, they are put in a row. That is, we have a close packing in one dimension. If you have atoms in one direction, in one dimension, you will have a line, just one line, and since in solids the atoms must touch each other, here every atom is touching the adjacent one. As you can see here, every atom touches its neighbor, so this is an arrangement in one dimension. So we say close packing in one dimension is all atoms or molecules or all constituent particles, we imagine them to be spheres and we imagine that they are all joined together to form a single row. Now is the time to introduce the concept of a coordination number. The coordination number is the number of atoms each atom touches or is in direct contact with. So how many atoms or neighbors does an atom touch? That is the coordination number. So in the case of close packing in one direction, if you see an atom in the middle, how many atoms is it touching around it? It is touching, for example, this orange ball. It is touching these two white balls. So it touches two neighbors and therefore its coordination number is 2. So coordination number in one dimension, you would have 2 and this is the arrangement. Atoms or molecules arranged in one or spheres arranged in one line. Let us now come to close packing in 2 dimensions. When you talk of 2 dimensions in close packing, we only had the length, let us say. So in 2 dimensions, you will have length and breadth. And if it is 3 dimensions, you'll have length, breadth and height. So let us now understand close packing in 2 dimensions. What are the possibilities? There are 2 possibilities as you see here in 2 dimensions. The first is where you have a square close packing and the second is where you have a hexagonal close packing as done in the diagrams. I'll just show you how this is done. I'll show you the first one, that is the cubic square close packing, or rather not cube, I should call it square because it will form a square. So in square close packing, as you know, the atoms, if you arrange them, they fall. Let me just do the one orange, one white, it looks prettier. Okay, so we have an orange here, a white here, and an orange here. Yeah. So do you see, I have arranged the atoms in such a way that every atom in the atoms of the second row, they fall straight above the atoms of the first row. Do you see this? They're falling right above the atom. If the first row was here, the second row atoms, they are in line with the atom. The first atom of the second row is in line with the first atom of the first row. And that is how it extends in 2 dimensions. The third line also falls like this. The fourth line, if I put, that will also be like that. So if you imagine it like this, let us say you will have similar atoms, the same arrangement. Every atom in every line is following the same pattern. It is following the same pattern, you see. So if I call the arrangement of atoms in the first layer to be A, then the second layer is also, or the second line is also A, the third line is also A. Why am I calling it A? Because it's a repetition of the same arrangement. Every new line is a repetition of the arrangement of atoms in the previous line. So whether you have this or you continue, it is A, right? It is the same. I'm talking of positions, not the colors. Or I'm just doing this for cosmetic purposes. Otherwise, they are all identical. So you would have A, the same pattern being repeated throughout. So such an arrangement is a square close packing. If you have the same number of balls, let us say you have 4 here and 4 here. So if this was 4 here too, it would have formed a square. Let us ignore, or let me overlap and show it to you like this. Yeah, do you see? It'll appear to you that it's forming a square now. Do you observe this? What have I done? I've arranged these 4 lines so I get a square, and therefore we call it square close packing. If I had moved to 3 dimensions, in the case of square close packing, what would I get if I followed this arrangement in 3 dimensions? Then I would have one layer of the square close packing in 2 dimensions. I would put a second layer of square close packing on top of the first layer. Now I'm getting not only length, breadth, but I've started getting height also. So now this is arrangement in 3 dimensions. So I put the second layer over the first, and then I put the third layer over the second, and I put, in order to form a cubic lattice. If you see, this will form a cubic lattice. And then I put the fourth layer over the third. And each layer, the balls of each, they've all moved. The balls of each layer fall over the balls of the previous layer, thus resulting in the formation of a cube. Do you see? I fix them in such a way that all of them should fall on the balls of the previous layer. And in that way, I will get a cubic lattice. Let me just arrange this carefully once more. Okay? So as I arrange these, it will result in the formation of a cube. Let me get the cube here. So you imagine if I had started filling up these balls inside the box, I could have fixed these balls inside this box. Do you see this? I could have fixed them. If I put one, then I put the second layer, then I put the third layer, each one would fall one above the other, and in 3 dimensions, the lattice, after having put 4 of those layers, I would get a lattice that is cubic, like a cube. So that would form a 3-dimensional square. It would not be, instead of square, it was square in 2 dimensions, but in 3 dimensions, it would be cubic close packing. So that arrangement is called cubic close packing in 3 dimensions, and we call it CCP. But I will be repeating the 3 dimensions again. Let us now understand the 2 dimensions first. This is the simpler one. Therefore, I just told you square close packing is nothing but 2 dimensions. And if you extend it to the 3rd dimension, you will get a cubic close packed structure. Coming back to 2 dimensions. The first arrangement was the square close packing. And let me come back to these balls now. I told you that I arranged the balls in such a way that each ball fell over the other. And therefore we were getting the square. Each one is forming a square. Do you see this? 4 balls, they form a square. 4 balls, they're forming a square lattice. But nature does not, do you see? On its own, the ball is trying to move into the groove of the previous 2 balls. It does not want to stay here because nature does not like wastage. Nature does not like wastage of space. If I try to give them a choice, okay guys, how would you like to, keeping this here, how would you like to arrange yourselves? If I give them oops, 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 oops. Now instead of forming this arrangement like this, if I gave these atoms a choice to move, if I gave them a choice to move, what would I notice? I would notice that if I gave them a free choice and I arranged them, the balls do not fall one over the other. The balls do not fall one over the other. If you imagine this to be the lowest layer now, do you see the balls above it would like to fall into the grooves of the previous 2? It would not like to come like this to form straight lines. Rather, the ball would want to fall inside the grooves. This is what nature likes. Nature on its own, if you allow the atoms to fix themselves, they will form these, they will fall into the grooves. They will not form the square close packing on their own happily. If we give them, because that is what nature, now this is the square close pack. I had to fix it. But if I gave it a choice of its own and I gave it a shove and to move on its own, they would like to fall into the grooves and form a better packing. Now if I look, let me just arrange this a little so that the structure becomes more visible to you, what I want to tell you, that they fall into the grooves. Now, yes. Now if you see these falling into the grooves, what do you observe? You observe, I would want you to observe this one ball here now in the center. It is being surrounded by 6 balls. Now this was row 1, A. The row second is not identical to A. Look closely. The second row is not identical. It would have been identical if it was right there. But it is not there. It is between the grooves of these two. So the second layer is not in line with the balls of the first line. And the third is not in line with those of the second one. But the third ball, the line of the third ball is in line with the line of the first ball. Do you see? This ball is in alignment, is in directly above the first layer, but the balls of the second layer are not above the balls of the first layer. So if I had a fourth layer here, the fourth layer would fall between these. And if the fourth layer would fall between these, the fourth layer would be, the ball here would be directly above the one before, in the penultimate line. So take a look here. In square close packing, the balls of one layer, the second ball is right above the ball, or rather the first ball of the second layer or line is directly above the first ball of the lower line. The first ball of the third line is also directly above the first ball of the second line. So we find that each ball in both directions is following the same pattern. And therefore you get, if you had only 3 and 3 here, you would have got a square close packed structure. Do you see this? So you would get square close packed structures. Do you notice them? They're moving because there's space here. So that is a square close packed structure. But if I gave them a little room, little more wiggle room to move around, and I gave them a little shake like you do in a tambula game, you know, and if I did that and I gave them a little choice to do what they like, I would notice that nature does not like the arrangement that was made. Nature likes the atoms not to be one above the other. Nature likes the atoms not to waste space. Therefore, the balls of the second line here, they will fall in the grooves of the first line. Instead of falling directly above the atom, it would prefer to fall into the groove. Have you seen the shopkeeper stacking oranges? Or how they do it? In the streets also, the vendor, he stacks oranges or stuff one into the groove of the other because there is no wastage of space in that arrangement. So what do we notice? That this is what nature likes. It doesn't like to waste space, and therefore the arrangement that you get is a hexagonal close packed structure. Why do we call it hexagonal close packed structure? Look at this ball here and see how many neighbors is it touching. It has around it, or take this white ball. Do you see 3 yellow balls, orange balls, and 3 white balls around it? So it is forming a hexagon. Do you see this? This white ball is being touched by 6 other balls on all sides. So these 6 balls, if you had their centers and made a line, make a line here, 2, 3, 4, 5, 6 would form a hexagon. So that results in the formation of a hexagonal close packed structure. So in hexagonal close packing, that is what nature prefers because there is less wastage of space in this arrangement. And since we are talking of the solid state, The hexagonal close-packed structures would be desired because solids need to be rigid, they need to be hard, and for that to happen, the atoms should arrange themselves in a more organized and a more compact manner. So this is a more compact arrangement. And you have this kind of an arrangement is known as a hexagonal close-packed arrangement. The hexagon because each ball is surrounded by 6 other balls, is being touched by 6 other balls. So, and if you look at the different lines now, the first line, whatever was the arrangement of atoms in the first line, you will notice that the atoms of the second line are not in alignment with the atoms of the first line. But atoms of the third line are exactly above the atoms of the first line. Do you notice this? The atoms of the second line do not fall above the atoms of the first line, but the atoms of the third line actually fall above the atoms of the first line. So if I call this line A, then the second line is not identical to A, and therefore I would call the second line B, and I could call the second line is not in alignment with this, so I would call the second line B, and I would call the second line would be B because it is not above the atoms of the first line, but atoms of the third line are exactly above the atoms of the first line. Therefore, this is again a repetition of A. So you have A, then you have B, then you have A, and then you again have B. Look here now. So do you notice? The balls of the first line and third line are identical. The balls of the second line and fourth line are identical. If you can notice this. First and third would be identical, and second and fourth would fall in line. So it means the first line and the third line are identical, second line and fourth line are identical. So we'll say if this is A, then second line is B. If then the third line is again A and the fourth line is B. So what kind of an arrangement do we have? The AB kind of an arrangement. In 2 dimensions, you will get an AB kind of an arrangement. The coordination number in the case of hexagonal close-packed 2-dimensional structure would be 6, and in the case of square close packing, the coordination number, if you see, every ball in the square close packed structure is touching 4 other balls in the same layer. And therefore, do you see this? Take a look at this ball here. It is, how many balls are touching it? 1, 2, 3 and 4. The 4 balls around it will touch it and the rest would not. Let me just bring this back again. So in a square close packed structure, this central ball is touching 1, 2, 3 and 4 balls. It touches directly 4 balls, that is 1, 2, 3, 4. It is not touching these balls are away from it. It is directly touching only 4 balls. So therefore, the coordination number in square close packing is 4 and the coordination number in hexagonal close packing, now we're talking only in 2 dimensions, is 6. So let us now come to close packing in 3 dimensions. If you had the cubic close packed, that is square close packing, if it is extended, you will get cubic close packing. As I explained to you, that if I put all these boxes of balls into this box, stacked one over the other in the same sequence, in the same pattern, I will get a cube, and that is cubic close packing in 3 dimensions, right? And which I showed you already. And now let us come to the hexagonal close pack, and this is a little more complicated, just as its arrangement was here, AB kind of an arrangement in 2 dimensions. Even in 3 dimensions, there's a very interesting pattern that you would observe. In the case of square close packed structure, let me show you that between the balls, do you observe the empty spaces between the balls? These empty spaces are known as voids. The ball is the constituent particle and the empty spaces between the balls are known as voids. That there's a void, there's a vacancy or a void. So when you stack them one over the other, we find that in the case of square close packing or cubic close packing in 3 dimensions, a ball falls over a ball and a void falls over a void. Do you observe this? If you see this, through this, you will be able to observe that the balls are falling on the balls and the voids are falling over the voids. You can actually see through. You can see through the voids. Do you see this? You can actually see through the voids because the voids fall on the voids and it goes right through. But in the case of the hexagonal close packing, we get voids, and the voids, first of all, the voids itself are of different kinds. And the second thing is that what kind of voids are covered and what are not. That brings about a variation in the kind of packing that you have with hexagonal, close-packed, 2-dimensional structures. So you get more of a variety with this kind of an arrangement. Why? Because first of all, it already is not following the pattern. The different lines itself had a difference in pattern, which gives it a possibility of variation. And then when you stack these layers one above the other, you can still have more variations. So let us understand the second layer and the third layer. I will not be doing it in this video. I'll do it in the next video because I would require a camera that will have to be focused. I'll need help with the photography there, where I could actually show you the stacking. So here you have to understand that you have this 2-dimensional arrangement, and this is the first layer of atoms. So now instead of we were first in 2 dimensions, we were taking different lines and we were following the patterns of different lines. For 3 dimensions, we will take the 2 dimension to be the base, and then the 3rd dimension is where we are looking at the difference in the structure. So the 2 dimensions we already know. In the case of square close packing, it is this, and when you put more and more layers, you will get a cube. That you already know. It is simple. The square close packing will give you cubic close packed lattice. That you understand. But what about the hexagonal close packing? The hexagonal close packing, when you put the first layer, you get this structure. But when you put a second layer over it, in order to understand that, you will notice that when I put a second layer over these atoms, the second layer, the balls of the second layer will again fall into the grooves of the first layer. Because unlike cubic packing, where we had ball over ball and void over void, in hexagonal close packing, ball will not fall over ball. Ball will fall on the voids of the previous layer. Although this is cubic, this should also have been hexagonal, but the balls will fall on the voids of the second layer. And since it falls on the voids of the first layer, you will get a difference in the arrangement. Let me just show it to you now. Okay. So now you see the hexagonal, these are all hexagonal close packed structure. This is the first layer. So now we will take the 2-dimensional layer to be A. Now this entire layer is A, it is HCP, that is hexagonal close packed. And now I start arranging the second layer in 3 dimensions. So the second layer, as the rule goes, it follows the kind of arrangement that it was doing, that the balls of one line were falling into the grooves of the balls of the previous line. So when you make a second layer, the balls of the second layer will fall into the grooves of the first layer. So you have one ball here, you have one ball here. I even put a pen here so that they don't move. Yeah. So do you see the second ball goes here, the third goes here, the fourth. Now what is happening? We've made the first line of the second layer. Now this first line is falling into the grooves of the first layer. Do you see? The second line of balls is falling into the grooves of the first layer. So again, following the pattern, this falls here, this falls here, this falls here. Automatically it takes its place into the grooves of the previous layer. Do you notice this? And now I've got hexagonal close packing in the second layer too. Do you notice this? Now I have the hexagonal close packing in the second layer. The first layer already was hexagonal close packed. Now the second layer has come in, which is also hexagonal close packed, but the balls of this layer have fallen into the grooves of the previous layer. Now, if you look carefully, can you see that from here, if you look down, you can see the table which is black down there. Do you see the black glass? The table is black. So from here, this hole, you can see a void is falling over a void. Do you notice this? And it's the same here. A void is falling over a void. So you can see the table under these voids. Such voids where a void falls over a void is known as an octahedral void. And if you notice that in this layer, the void, this was a void. In the first layer, you had two types of voids. Here you had a void, and you had a void here and a void here. The balls fell into the voids of the first layer, but the balls of the second layer did not cover all the voids. There are still some voids left, which are still voids through and through. Do you notice this? We had balls. Each ball is covering a void. It is falling on a void. Do you see? The center of this is falling over a void, but it is covering one void, this one, but it is not covering this void, and it is not covering that void. It is falling here, but those two voids, if you see there, it goes right down. You can see the table, void falling over void, void falling over void, void falling over void, right? So the second layer shows that although it forms a hexagonal close packed structure, now the voids that we obtain after the second layer are of two types. One is the tetrahedral void. A tetrahedral void is this, where you have three balls at the bottom and this form falls over it. So it forms a tetrahedron. A tetrahedron has four corners, and the four corners are a triangle and one ball in the center of it. So that is what is happening here. A triangle in the bottom, and one ball fell into this triangle in the bottom, and one ball that fell over it will cover it, and therefore that void, it is trapping this void and making the void, the shape of the void becomes tetrahedral. But this void below it and a void falling above it, this is formed where you have three balls in one direction. Do you see? If I remove these three balls, you had three balls like this, 1, 2, 3 in the basic layer. In the second layer, I have where you had one ball, you get two balls, and where you had two balls, you get one ball. So a triangle in this direction in the base is being covered by a triangle on the upper layer in this direction. So a triangle of three balls like this in the first layer being covered by a triangle of three balls in the second layer. Do you notice this? So this results in the formation of a void over a void, and that void is known as a tetrahedral void. So you get two kinds of voids in this. The octahedral void, which is this, and the tetrahedral void, which is formed when one ball of the second layer covers a void of the lower layer. It results in the formation of a tetrahedral void. But when the three balls of the lower layer are covered by three balls of the second layer and none of them cover a void, that new void that is created, a longer void, that is known as a octahedral void. So this void falling over a void will form an octahedral void, and this void, which is formed by three balls in the first layer covered by one ball covering a void and thereby sealing it, this is a tetrahedral void. So that is how you get two kinds of voids when you get the hexagonal close packed layers. So we have one hexagonal close packed layer, which was A. Now we will call the layers as A and B. So the first layer was A, and the second layer is not in line with the first layer. Therefore, the second layer is B. Right? I hope you understand. The second layer is not in line with the first one. Therefore, the second layer will be known as B. This is layer B. And you get two kinds of voids, the tetrahedral void and the octahedral void. And now when you get the third layer here, the third layer would be of two types. One
is where, do you see here below this is a tetrahedral void. There's one ball and three balls. So you see these three balls and there's a ball right under this. So this is forming a tetrahedral void. So now my next layer could either be formed by covering a tetrahedral void and then extending the structure or, do you see this? Now what did I do? For the third layer, I put a ball on the tetrahedral void and made the third structure. Or there was an option I had. Instead of covering the tetrahedral void, I had a possibility, I had a chance to instead cover an octahedral void. And if I covered an octahedral void in the third layer, I would again get the hexagonal close packing, but this time I'm covering different kinds of voids. So this structure will be different from the structure you would get by covering the tetrahedral voids. But this I'll explain it to you tomorrow when I have a little help with someone who'll help me with the camera. Then I could explain and show you the different types of voids too. Right now, just understand these two layers, that you get this bottom layer, we'll call it A, and the second layer we'll call it B. And as a result of layer B, which does not fall directly over the balls, therefore it is layer B, we get two kinds of voids, the tetrahedral void and the octahedral void. Here it is also important to mention one thing, that if the octahedral voids, whatever is the number of octahedral voids in such an arrangement, let us say that the total number of spheres in the close packed structure is n. Then the number of octahedral voids would be equal to this number. It would be equal to n. And the tetrahedral voids, on the other hand, are more. Therefore, the tetrahedral voids would be 2n in number.
So what did we understand from this? That we now look at this structure here. You had the hexagonal close packed as A, that is the first layer, which was the one that is with solid lines that I've made the solid circles. And the second layer I've drawn with these dotted circles. And these dotted circles, when they fall, now I want you to notice that three balls in the bottom are being covered by this one ball here. So this will result in the formation of a tetrahedral void, as I showed it to you here also. And this is a tetrahedral void, and where a void falls over a void, that would be an octahedral void. So if I had to make these structures like this, if this is the bottom layer, three balls is the bottom layer. If one ball falls over it, it results in the formation of a tetrahedron. Do you see this? It's like a pyramid, a tetrahedron. And this void inside, let me use orange balls. Right. So this void that you observe now, this void that you see here would be a tetrahedral void in the middle. So it's a tetrahedral void. And if I had three balls in the bottom layer and three balls in the upper layer, right? And now the three balls, if they are in this direction, the second layer I have with three balls, this has one ball on top and this has two balls, and I join them like this. If I join them, that results in the formation of an octahedral void. Can you see through and through? You will see a void through this. Yes, you can see through and through. You can see my hair, the black dot that you see in the middle, right? That is where you can see light passing through. It means there's a void throughout. The three balls in one direction covered by three balls in the other direction. That is, you had one on top here, you have two on top here. So you mix them, and in the middle you have a huge void. Where can I show you the black color? Yes, you can see through and through. That forms a void, right? So this kind of a void which is formed when you have three balls of the lower layer covered by three balls in the opposite direction, it results in the formation of a void which is known as an octahedral void. But if you had three balls in the lower layer covered by one ball in the second layer, it would result in the formation of a tetrahedral void. So this was the arrangement in 2 dimensions and 2 layers of it. In 3 dimensions, and that is in 2 layers only. Now in the next video I'm going to do the 3rd layer also, and then understand the variations that are based on that 3rd layer. I gave you a little hint right now, but we'll go into more details if possible with the camera and the walls. If I can explain it to you, I'll definitely try to. With that, I'll put an end to this video. I'll just finish it right here. If you found it helpful, please give it a thumbs up, subscribe to my channel, recommend it to your friends, and please keep returning for more videos in chemistry. Thank you for watching, and bye-bye for now.